Chapter 14 of Astronomy, the Science of the Heavenly Bodies, by Todd. Newton and gravitation. So all of Kepler's laws could be embodied in a single law of gravitation toward a central body, whose force of attraction decreases outward in exact proportion as the square of the distance increases. Only one farther step had to be taken, and this the most complicated of all. He must make all the bodies of the sky conform to his third law of motion. This is, action and reaction are equal, or the mutual actions of any two bodies are always equal and oppositely directed. There must be mutual attractions everywhere, Earth for Sun as well as Sun for Earth, Moon for Sun and Sun for Moon, Earth for Venus and Venus for Earth, Jupiter for Saturn and Saturn for Jupiter, and so on. The motions of the planets in the undisturbed ellipses of Kepler must be impossible. As observations of the planets became more accurate, it was found that they really did fail to move in exact accord with Kepler's laws unmodified. Newton was unable, with the imperfect processes of the mathematics of his day, to ascertain whether the deviations then known could be accounted for by his law of gravitation. But he nevertheless formulated the law with entire precision, as follows. Every particle of matter in the universe attracts every other particle, with a force exactly proportioned to the product of their masses, and inversely as the square of the distance between their centers. The centuries of astronomical research since Newton's day, however, have verified the great law with the utmost exactness. Practically every irregularity of lunar and planetary motion is accounted for. Indeed, the intricacies of the problems involved and the nicety of their solution have led to the invention of new mathematical processes adequate to the difficulties encountered. And about the middle of the last century, when Uranus departed from the path laid out for it by the mathematical astronomers, its orbital deviations were made the basis of an investigation which soon led to the assignment of the position where a great planet could be found that would account for the unexplained irregularities of the motion of Uranus. And the immediate discovery of this planet, Neptune, became the most striking verification of the Newtonian law that the solar system could possibly afford. The astronomers of still later days, investigating the statelier motions of stellar systems, find the Newtonian law regnant everywhere among the stars, where our most powerful telescopes have as yet reached. So that Newton's law is known as the law of universal gravitation, and its author is everywhere held as the greatest scientist of the ages. Newton's Principia may be regarded as the culminating research of the inductive method, and further outline of its contents is desirable. It is divided into 3 books, following certain introductory sections. The first book treats of the problems of moving bodies, the solutions being worked out generally and not with special reference to astronomy. The second book deals with the motion of bodies through resistant media, as fluids, and has very little significance in astronomy. The third book is the all-important one, and applies his general principles to the case of the actual solar system, providing a full explanation of the motions of all the bodies of the system known in his day. Anyone who critically reads the Principia of Newton will be forced to conclude that its author was a genius in the highest sense of the word. The elegance and thoroughness of the demonstrations and the completeness of application of the law of gravitation are especially impressive. The universality of his new law was the feature to which he gave particular attention. It was clear to him that the gravitation of a planet, although it acted as if wholly concentrated at the center, was nevertheless resident in every one of the particles of which the planet is composed. Indeed, his universal law was so formulated as to make every particle attract every other particle, and an investigation known as the Cavendish experiment, a research of great delicacy of manipulation, not only proves this, but leads also to a measurement of the Earth's mean density, from which we can calculate approximately how much the Earth actually weighs. Another way to attack the same problem is by measuring the attraction of mountains, As Maskelyne, Astronomer Royal of Scotland, did on Mount Schiehallion in Scotland, which was selected because of its sheer isolation. The attraction of the mountain deflected the plumb lines by measurable amounts. The volume of the mountain was carefully ascertained by surveys, and geologists found out what rocks composed it. So the weight of the entire mountain became pretty well known, and combining this with the observed deflection, an independent value of the Earth's weight was found. Still, other methods have been applied to this question, and as an average it is found that the materials composing the Earth are about 5.5 times as heavy as water, and the total weight of the Earth is something like 6 sextillions of tons. What is the true shape of the Earth? And does the Earth's turning round on its axis affect this shape? Newton saw the answer to these questions in his law of gravitation. A spherical figure followed as a matter of course from the mutual attraction of all materials composing the Earth, providing it was at rest, or did not turn round on its axis. But rotation bulges it at the equator and draws it in at the poles, by an amount which calculation shows to be in exact agreement with the amount ascertained by actual measurement of the Earth itself. Another curious effect, not at first apparent, was that all bodies carried from high latitudes toward the equator would get lighter and lighter, in consequence of the centrifugal force of rotation. This was unexpectedly demonstrated by Richter when the French Academy sent him south to observe Mars in 1672. His clock had been regulated exactly in Paris, and he soon found that it lost time when set up at Cayenne. The amount of loss was found by observation, and it was exactly equal to the calculated effect that the reduction of gravity by centrifugal action should produce. Also, Newton saw that his law of gravitation would afford an explanation of the rise and fall of the tides. The water on the side of the Earth toward the Moon, being nearer to the Moon, would be more strongly attracted toward it, and therefore raised in a tide. And the water on the farther side of the Earth, away from the Moon, being at a greater distance than the Earth itself, the Moon would attract the Earth more strongly than this mass of water, tending therefore to draw the Earth away from the water, and so raising at the same time a high tide on the side of the Earth away from the Moon. As the Earth turns round on its axis, therefore, two tidal waves continually follow each other at intervals of about 12 hours. The Sun, too, joins its gravitating force with that of the Moon, raising tides nearly half as high as those which the Moon produces, because the Sun's vaster mass makes up, in large part, for its much greater distance. At first and third quarters of the Moon, the Sun acts against the Moon, and the difference of their tide-producing forces gives us neap tides, while at new moon and full, Sun and Moon act together and produce the maximum effect known as spring tides. Newton passed on to explain, by the action of gravitation also, the precession of the equinoxes, a phenomenon of the sky discovered by Hipparchus, who pretty well ascertained its amount, although no reason for it had ever been assigned. The plane of the Earth's equator extended to the celestial sphere marks out the celestial equator, and the two opposite points where it intersects the plane of the ecliptic, or the Earth's path around the Sun, are called the equinoctial points, or simply the equinoxes. And precession of the equinoxes is the motion of these points westward or backward about 50 seconds each year, so that a complete revolution round the ecliptic would take place in about 26,000 years. Newton saw clearly how to explain this. It is simply due to the attraction of the Sun's gravitation upon the protuberant bulge around the Earth's equator, acting in conjunction with the Earth's rotation on its axis, the effect being very similar to that often seen in a spinning top or in a gyroscope. The Moon moving near the ecliptic produces a precessional effect, as also do the planets to a very slight degree, and the observed value of precession is the same as that calculated from gravitation, to a high degree of precision. Newton died in 1727, too early to have witnessed that complete and triumphant verification of his law, which ultimately has accounted for practically every inequality in the planetary motions caused by their mutual attractions. The problems involved are far beyond the complexity of those which the mathematical astronomer has to deal with, and the mathematicians of France deserve the highest credit for improving the processes of their science so that obstacles which appeared insuperable were one after another overcome. Newton's method of dealing with these problems was mainly geometric, and the insufficiency of this method was apparent. Only when the French mathematicians began to apply the higher methods of algebra was progress toward the ultimate goal assured. D'Alembert and Clairaut for a time were foremost in these researches, but their places were soon taken by Lagrange, who wrote the Mécanique analytique, and Laplace, whose Mécanique céleste is the most celebrated work of all. In large part, these works are the basis of the researches of subsequent mathematical astronomers who, strictly speaking, cannot as yet be said to have arrived at a complete and rigorous solution of all the problems which the mutual attractions of all the bodies of the solar system have originated. It may well be that even the mathematics of the present day are incompetent to this purpose. When the brilliant genius of Sir William Hamilton invented quaternion analysis and showed the marvellous facility with which it solved the intricate problems of physics, there was the expectation that its application to the higher problems of mathematical astronomy might effect still greater advances, but nothing in that direction has so far eventuated. Some astronomers look for the invention of new functions with numerical tables, bearing perhaps somewhat the relation to present tables of logarithms, sines, tangents, and so on, that these tables do to the simple multiplication table of Pythagoras. End of chapter 14.